So we're on to how do power meters work part 2. And so we'll go ahead and jump right in. We were talking about this circuit before, right? In the real world, we have wire losses. And so we need to accommodate for those, right? And so let's just say for the purpose of this, just to, expand, that this is 14 AWG wire, from right here, right? This is 14 AWG wire. And so is this, and that each one of these is 1,000 foot long from point 1 to point 2 and 1,000 foot long from point 3 to point 4. All right. Now, I'm going to go into this a little bit further, but the resistance of wire can be calculated as well. 14 AWG wire is a cross-sectional area of this of just over 2 millimeters squared, and then we would use the resistance right here. This is rho of copper, and so copper has a known resistance. So we're gonna get into that, right? So the cross-sectional area is, if I took this wire and I laid it flat, it would be a cylinder. I would cross it right in half, and the cross-sectional area, right, the area of a cross-section of that wire is going to be calculated by the area of a circle, right? And so the area of a circle, well, we just need the diameter or the radius. And here you can look up 14 AWG wire. The diameter and the radius is all figured out right here. It's this little number, 1.628 millimeters. You take that is the radius. I'm sorry, that is the diameter. So what we need is area equals pi r squared. We need to get that to a radius. So you take the diameter, divide it by 1/2, which is what we're doing right there, times 0.5. That gets us a radius of 0.814 millimeters. Plug that bad boy into this equation right here, and you've got that squared times pi, and you get to this right here, okay? 2.08 millimeters squared. And we can take that and we can plug that into our millimeters squared. We know that this is 1,000 meters, or excuse me, 1,000 feet long. We can plug that in down here, and then we just have an ohmic value right here. We can figure out the rest of it, okay? So let's go ahead and figure all this into it. So our in red right here is our 1,000 feet to meters. That's what this is. This is, well, we need, the bottom of this row equation was 1 meter. So we need to get to meters. So all of this, on the left right here is converting to meters. Okay. And then we have this cross-sectional area that's right here. And then the resistance of copper is rho, which is right here. And, when you go ahead and you multiply all this out, what you're going to end up getting is, and just for the sake of some of you math people, feet cancels with feet, inches cancels with inches, centimeters cancels with centimeters, meters cancels with meters, meters squared cancels with meters squared, or excuse me, millimeters squared, both cancel out. The only unit you're left with is that one little ohm, right? So you multiply all the numbers across. Don't forget you got 100 on the bottom and a 2.08 on the bottom. So you have to divide those out, and you get this right here. So that is the resistance of 1,000 feet of wire, right? And we have 2 of those. So we have this equation right here. We had our original equation, which is 3,000 ohms, the 2.5 and the 2.5 ohms. Add all that together, and what do you get? You're going to get very close to the same number, 3,005. We only went up by 5 out of 3,000, right? So it was pretty negligible. And instead of 3 milliamps, we have 2.994 milliamps, which is a measurable amount. It's 4 significant digits instead of 3, but it is a measurable amount, and you may see that on your multimeter as a difference, right? And so there is a difference, and that is important. So let's talk about a few things. Ohm's law: the voltage drop across the resistor is equal to the current flowing through it multiplied by its resistance. That is Ohm's law. I would almost say it would be better to state a device with an ohmic value instead of a resistor, because it could be anything. This wire has an ohmic value through it, and there is a voltage drop across the wire. And then these other two laws, are Kirchhoff's current law and Kirchhoff's voltage law. So we know that everything around the loop has to add up. So you have a little bit of a voltage drop in this wire, a little bit of voltage drop in this wire, a little bit of voltage, or primarily the majority of that voltage drop is across that resistor, right? Why is this important? With this information, we can calculate the voltage drop of those wires, also of that resistor, and we understand that all copper and aluminum, all conductors have a voltage drop across them when running a current because they do not have a 0 ohm resistance across them. They have a known resistance, and that is extremely important when we deal with the current, shunt, and the voltage divider, which is going to be in the next video.